All right, so I had a question about the difference between the branch and the jump. So what I have done is set up a set of code here, and the code contains a branch not equal, a branch equal, and a jump. So what we're going to do is first move through the code in order to identify what's really happening in this code. Then we're going to encode both of the branch instructions as an example. Now I've specifically set this up so that top is referenced with this branch equal, so this branch equal is going to go backwards. And then the branch not equal refers to end, and I haven't labeled any of those end. If I leave it like this, we're going to have a problem encoding this. It's also going to be an error when you assemble it, because we have a missing label. So, as written, we'd have a problem. End has to be somewhere. Now, since the top goes backwards, I'm going to choose, and this is my prerogative, that end will be the jump instruction. Okay? And we'll talk about the ramifications. So, this branch not equal is a forward jump. The branch equal is a backwards jump. All right? So, this jump long distance is going to be a little trickier because we're going to need more information. However, to encode the branches, we have all the information we need because we have end, and we have top and top. So that's all we need. Had I not this end, you would not have enough information to solve the problem. All right. So first of all, we'll walk through the code. We have a simple R-type instruction. This is not really meant to do anything. It's just an example. Then we get to the branch not equal. So, branch, branch if not equal. Okay, this is the BNE. And I want to go into detail about what that means because I've had some questions on it. So, if the contents of R6 is equal to, and I'll use that double equal sign as the Boolean test like we do in C, if R6 is indeed equal to R7, okay, R6, if this is the case, well, we're only going to branch or fork if they're not equal. Then we go to next. The next instruction. It's as if it didn't happen. Now, if R6 equals 9 and R7, so this is a different case, and R7 equals negative 30,000, they're not equal. So the condition is branch if not equal. Here, R6 bang equals R7. So we go to the label. Okay? And maybe it's called label, maybe it's called end, maybe it's called long distance, maybe it's called top, whatever label is in there. So that's the branch not equal. If they're equal, nothing happens. Just ka-chunk, ka-chunk, ka-chunk. If they're not equal, we're going to branch. And the way I explained this before, it's like if you have a stick and then a branch off of that tree, well, that's what a tree does to make itself more fuller. It juts out another way. Just like a tree grows and then it has a branch this way and it has a branch this way. We're going to branch or do something different if they're not equal. All right? Then that's not equal. For the branch equal, just the opposite. So I won't take time to explain that, but I'll talk about it and not explain it. Branch equal. Now we're going to branch or go somewhere else if they are equal. So if register 4 contains 1,000 and register 7 contains 1,000, they are equal, so we will branch. Okay? And when I say branch, I mean go somewhere else. Where do I go? Well, in this particular case, I go to the instruction labeled top. This is an argument of branch equal. This is a label for the line. It only identifies where I hop to or where I branch off to. Lots of times, jump and branch are used interchangeably. And so I heard a student today saying, jump. Well, we're going to be careful only because of the instruction set that Hennessy and Patterson gave us for MIPS, which is branches are conditional and jumps are unconditional. Now, in other architectures, you'll hear people use them interchangeably. But think about a branch as a conditional thing. And, as we'll see, a branch is relative. It is relative to the instruction. And, as we said before, the default instruction is the reference point. All right, so now let's encode branch not equal. Our first question is, what is the format? Is it a J format, an R format, or an I format? Well, it doesn't have a constant here, but it will have a constant here. So it has an immediate. And so we can either look that up or we can think about it. It's going to have a number in here. So we use the 4-segmented I format, which has op, rs, rt, and then the constant or immediate. Okay? Then I'm going to grab my card and always have your card quick at the draw. So, what is the opcode for branch not equal? There's no way for you to know that unless you look it up. You need a reference. So, branch not equal, that says it's a 5. I'm going to have a 5 there. What I could have done without looking up the card is I know that 6 and 5 are going to go here. Now, the last number, the constant, the immediate, is going to be relative, not to the branch itself, but to the default instruction, which I've called the anchor. Okay, this is your anchor instruction. This is where it would go if it didn't branch. Okay, so the question is, where relative to the default instruction do I go? Well, here I'm going to go to end. So this is my anchor. I'm going to need to go 1, 2, 3 instructions. You close the door, please. 1, 2, 3. Now that's going to be 12 bytes. But in order to increase our distance that we can branch, we don't put a 12 here. We put number of instructions. So I'm going to put a positive 3 in there because I am going forward. Forward is positive, negative is backward. All right, let's go to this branch equal top. Now, I can immediately put a 4 and a 7 in there because I'm going to read it off the registers. I have to look up the opcode, and the opcode is 4. Okay, remember this is 6 bits. This is 5 bits. This is 5 bits. And if we add that up, that leaves us 16 bits. Okay? And then the immediate, relative instructions. So, the anchor instruction for the branch equal is the AND. Okay? So, that's the default instruction, and we count relative to the default instruction. So I know it says top here, but I need to start counting to top from the default instruction. So I am going to go negative or back 1, 2, 3, 4, and now I get to top. So I'm going to put a negative 4 in there. Well, hopefully you can do this because it's easy. I need 6 bits for the 4. So it's going to be 0, 0, 0, 1, 0, 0 for the 4. Now, that's 6 bits. I also have a 4 here, but it's a 5-bit field. So I'm going to have 0, 0, 1, 0, 0. Again, 5 bits. It's interpreted as a positive unsigned integer. Then I need a 7. And so I'm going to do 0, 0, 1, 1, 1 here. Now we've got the negative 4. Well, we know it's going to have a bunch of 1s. Okay? And its magnitude is 4. What I think about this is, if they were all 1s, it would be a negative 1. So I need to go 3 more up from that. So all 1s is negative 1. So I need to knock out a 3 here, because these get us closer to negative numbers. The more zeros there are here, and remember this field is extended down, so that is going to be a negative 4. Now what's the other way to do it? I'm going to, you've got a number of different things. 4 is 0, 1, 0, 0. I could invert all the bits and add 1. So 1, 0, 1, 1. Now I add 1, and I get 0, carry the 1, 0, carry the 1, 1, carry a 0, and then a 1, and then I've got leading 1s. Did I get the same thing? I did. The other way is to take 0, 1, 0, 0, and I keep the zeros. I start marching this way, and I keep all the zeros until I hit the 1. I keep that 1, then I invert all the rest of the bits. And so here I get 1, 1, 0, 0. Here I get 1, 1, 0, 0. Those are the 3 different ways to do 2's complement negation. All right, then if I had to, I could start doing this in hex. So I know I've written this down for space reasons, but in hex I've got to divide by 4, okay? And then I've divided this by 4, but I hit my 16 delimiter, and so that's good because I know that 16 should be 4 hex digits. All right, so I've got a 0x, and then I've got a 1, and I've got a 0. Then this guy here is an 8, I think. And then this is a 7. Then this is an F. Then this is an F. This is an F. And then this, gentleman, is a
C.
C, good job. All right. So that's how I convert it. All right. So hopefully that tells you how the branches work and then how we encode them. Remember, the branch instruction itself, whether it's equal or not equal, is going to have an anchor, which is the next instruction. If the condition is not met, ka-chunk, just as if that branch didn't exist. If the condition is met, equality or non-equality, then it goes somewhere. Where does it go? Well, you look for the label. And then if it's forward, it's going to be the number of instructions forward positive. If it's going backwards, it's going to be a negative number, and it's a negative number of instructions. Not from the branch, from the anchor, from the default instruction. All right. So now we want to encode the jump. Well, we know it's going to be a jump format. And if we look on our card, the jump format's a little bit different. It has an op and a target. And the opcode is 6 bits long. So you can see a symmetry that all op fields are always 6. So if you're decoding a instruction, look at the first 6 bits. If the first 6 bits are a 2, you know it's a jump instruction and you know how to segment out the rest of the instruction. If the op field contains a 0, you know it's an R format. So you got to chop it up into 5 more. If it's anything other than that, it's an I format, so you need to chop it into 4 fields. And then those are listed at the bottom of your card. Target. Okay? This is going to be 26 bits long. Now this is not relative. This is absolute. And so if I gave you this information, you should start screaming, yelling, coming to my office with pitchforks and torches and say, how do you expect me to solve this? I cannot solve this because I don't have enough information. Well, what you need to know is where these instructions are stored in memory. Okay? So let's say somewhere down here we've got a sub instruction. Okay? And that has the label long away, or long distance. Okay. Anyway, so this is long distance. But I'm not going to tell you how many instructions are there between. Maybe there's thousands upon thousands of instructions. Maybe there's hundreds of thousands of instructions. I have to tell you where in memory this is stored. So, let's say that I've got my code, and I'm going to have an address 0xb00F, and then 8000. Okay? Boof. Okay? So, let's say, and I'm only going to write the instructions here. So this is the branch equal. Okay? Then this is going to be the and this is going to be the jump. Okay? So this is going to, and I'll just write the last 4 digits. This is going to be at 8004. This is going to be at 8008. Okay? And what you should be clamoring for is, what is the address of the instruction sub 123, which is labeled long distance? Now it could be hundreds of thousands of instructions away. So let's say that it is very far away, and the sub 123, which has the label long distance. We want to go from here, okay, jump long distance. We want to go from boof 8008 all the way up to here. Well, I have to tell you where that is. Okay? Yes, I will tell you where it is. It is in 0x beef. Okay? Now you guys know I like pork, but you can't spell out pork with hexadecimal numbers. And 101F, let's say. Okay? Now, the jump instruction starts with boof. Okay? And it's at 8008. We know it's divisible by 4. What goes in these 26 bits? Beef 101F is a binary, is stored as a binary number. So okay, so beef one, I gotta leave me some space, 0, 1. Oh, did I put an F here? I should get an F for this example. I can't have 01F, I have 018. Okay? So I've put an invalid address for an instruction. Hopefully you at home were screaming and yelling at the screen, maybe even breaking the screen, throwing something at it. All right, so that's the only valid instruction. So that's where I want to go. Long distance is stored at this absolute address. So let's write out this in binary. We have 1011, then 1110, 1110, 1111. Okay? Now this guy, I'm running out of space here. So this is 0001, 0000, 0001, and then 8, which is 1000. Okay? Opcode for jump is 2. So the 6 bits will be 0, 0, 0, 0, 1, 0. That's 6 bits. That's what will be here. Now what do we put in the target? Okay? That was to show it's far away. Well, I don't need to encode these two zeros. Why? Because I know, unless Old Man Will makes a mistake and puts it as an F, I know that the target is going to have a 0 and a 0 at the end. But I only have 26 bits. So that means I have to take the next 26 bits. I don't take the last two because they are superfluous, meaningless, not needed. So 26 bits ends up being this amount. And that's what I encode. So if I were to encode this as hex, I can't start here and put the hex. I actually have to start down here and then divide it like this. Like that. But this is the permutation of bits that would go in there. There are 26 bits here. That's what would go into the target field. And then, okay, then let's put this, okay, so this is going to be 3, and that's going to be B. Yep, that's B, and that's B, and that's C, and that's 4, and that's 0, and then that is going to be 6. Okay? So whatever I put in this target, I could put 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 0, 0, 1, 0, 1, 1, 0. I could put these numbers in there, or I could express it with this hexadecimal number. Okay? So I know this video is getting long, but I want to do one more thing. Okay? Let's go in the reverse. Okay? Let's go in the reverse. So, if I gave you a jump instruction, give me the absolute address of where it goes. And let's stop the video.